Okay, so the first section of the notes, we're going to look at just simplifying. We're not solving, okay? So simplifying, we're going to look at the index of our radical, and that is the number of pairs you want to make, or the number of the same factor that you want to make. So if I have a square root, you want to find pairs. If I have a cube root, you want to find groups of 3, okay? Hopefully you remember this. Always check to see if it's a perfect square first. Alright, square root of 72, hopefully you know that is not a perfect square. So how would I simplify square root of 72? I do my prime factorization, right? So I split 72 into 2 and 36. 36 splits into 2 and 18, which splits 2 and 9, which splits 3 and 3. Okay, so I said index and radical. Do y'all know what I'm talking about whenever I say that? Index. What's my index? Y'all know that? So if I have that, this is my radical. My index is the number that sits in that little bitty spot. That tells you your root. So when it says nth root, that's your root. Okay? Whatever goes inside your radical is called your radicand. So if I use these terms, that's what I'm talking about. Alright, so my index is 2. I want pairs of 2, so I have a pair of 2 and a pair of 3 with a 2 left over. So what is that going to turn into? 6 square root of 2. Alright? Now I should be able to look at the next example, square root of negative 36, and automatically get to my answer, which is what? 6i. Now, I'm not doing plus or minus because I'm just simplifying, okay? If you are solving, then you have your plus or minus. But if you're just simplifying, you're good to just leave it like that. Now, if I have the cube root of 80 into the 5th, okay, I'm still going to do my prime factorization for 80. But now instead of pairs, I'm going to do groups of 3. So 80 is going to split 2 and 40, which will split 2 and 20, which will split 2 and 10, and then 2 and 5. So I have a group of 3 2's with a 2 and a 5 left over. Alright, but I also have to take care of that n to the 5th. So that exponent on your variables tells you how many you have. So if I have n to the 5th, then I've got 5 n's. And I'm going to treat my variables the same way I would with those 2's. I want groups of 3. So I can have one group of 3 and I have 2 n's left over. Okay? So what I pull out is I had my 2 and I had my group of n. And then I'm going to have the cube root. I have a 2 and a 5 left over, so that becomes 10. And I have 2 n's left over, so that becomes n squared. Okay, your variables will tell you what your exponent is when you box them. So if I have 2 n's left over, what's n times n? N squared. Okay? Now, if you like to check your answers, I skipped over this for the first one. All you have to do is type in, like if you have something simple like this, square root of 72. And then type your answer, 6 square root of 2. Gave me the same decimal. So I know they're equivalent. Now, if you don't simplify it all the way, then your decimals might still be equivalent, so you just have to make sure you're simplifying. Now, if you wanted to check something like this, okay, you obviously can't put an n in here, but we know how to store a value for x, right? So pick any number you want. I would not do 0. I always do 5. Okay, say 5, store for x, and that just puts some placeholder for my variable. Okay, so I can do the cube root, which there's 2 ways to do the cube root. I've taught y'all math 4, but if you want to look, if you look next to the 7, you've got that button, which usually puts you in an exponent. Well, the inverse of that is an nth root. So if you want to do the index and then that button, that gives you the cube root. So I've got 80 x to the 5th. That's my original. Y'all follow me? Okay. Get that decimal, and then I'm going to have my answer 2x times, I'm going to do it again, my index, cube root of 10x squared. Should work. I haven't checked it, but it should work. Yeah. So you just store a value for x, and that's how you can check it, okay? If you wanted to. As long as your decimals are the same, then you're on the right track. Alright, so if I've got the square root of 81 p to the 4th cubed, the square root of 81 I know is what? 9. If I have the square root of p to the 4th, that means I have 4 p's. How many pairs could I make? 2. If you need to write that out, you can. So p squared would come out. I don't have any p's left over. And then I've got q's. I've got 3 q's. I can make a pair with 1 left over. So I bring out a q, and then I've got the square root of my remaining q. So 9p squared times the square root of q. So if you wanted to check, you would just have x and then you would have y. Okay? Your variable doesn't matter, but remember that you can press that variable button multiple times if you need to. Okay, are we good so far? Alright, the 4th root of 96. Okay, so the reason that I showed you this on the calculator is so that you know how to do anything other than a cube. So I'm going to do my index first, 4, and then I'm going to do 96. I'm going to check to see if that ends up giving me a perfect number, which it does not. Okay, but that's how you're going to check it. So that means I'm going to do my prime factorization. 96 will split into what? And then that splits. And then 2 and 12, 2 and 6, 2 and 3. So I'm going to do groups of 4 because that's my index. And I have my 2 and my 3 left over. So what would my answer be? 2 times the 4th root of 6. Okay, now compare that to the next example. What do you notice? It's just negative, okay? That negative placement is important. That's on the outside of the 4th root of 96, okay? Well, we know the 4th root of 96 we just found was 2 times the 4th root of 6. If the negative's on the outside, then it's going to just turn into negative 2 4th root of 6. But we're going to look in a second for the next section what that negative affects depending on is it on the outside or the inside. Okay? Had it been on the inside, what would have happened? You would have had an I. You would have had your imaginary because it's a 4th root of a negative. Okay? Alright, now what if I want to actually do operations with radicals? Okay? Anytime I add or subtract, whether it is constants and variables or real and imaginary, you can only do like terms when you're adding and subtracting. Okay? So if I'm looking at 5 squared root of 2 minus 11 squared root of 18 plus 4 squared root of 50, the radicals are going to make it like terms. Okay? So the number, the radicand, is what's going to allow you to add or subtract. None of these are the same. So I'm going to have to simplify what I can to see if I can form like terms. Okay? Well, 5 squared root of 2, I'm not going to be able to do anything with. That's already simplified. But if I have negative 11 square root of 18, I can take this 18 and I can break it down. 18 will break into 2 and 9. 9 will break into 3 and 3. So I'm also going to break down that 50 in the same step. That breaks 2 and 25, which breaks 5 and 5. Okay, so that 5 square root of 2, I'm going to bring down But this negative 11 square root of 18, that square root of 18 simplified to 3 square root of 2, right? So I need to take care of this negative 11 and this 3. What am I going to do with it? Multiply it. Okay, so this is going to become negative 33 square root of 2 plus 20 square root of 2. Y'all remember this? Okay. So if you already have a number outside the radical and you're simplifying a radical, you multiply whatever's on the outside. Okay? So now I've got 5 square root of 2 minus 33 square root of 2 plus 20 square root of 2. I'm going to treat the number in front of the radical like a coefficient, as if I'm adding 5x minus 33x plus 20x. Okay? If I'm adding variables, those variables don't change, right? So if I'm adding like radicals, my radicals do not change. Only what is considered the coefficient is going to change. Okay? So 5 minus 33 plus 20 is going to give you. And again, you could type your original, get a decimal, type your answer. You should get the same decimal. Okay? Alright. Now this next example, I'm multiplying radicals. You can do one of two things. You can simplify first and then multiply, or you can multiply, get a really large number, and simplify just at the end. Okay? It doesn't matter as long as you are always trying to simplify. I personally will simplify first. I don't want to multiply 32 and 72 and try to break that factor tree down. I personally do not. Okay? So if I'm doing 32, I know that'll split 2 and 16, 2 and 8, 2 and 4, 2 and 2. But I also have to consider my x's. I've got 5 of them. So I can do 2 pairs with 1 left over. Okay, so that 32x to the 5th is going to turn into what? Square root of. Okay, I'm going to take that, and if you want to write it in parentheses, you can. Sometimes you'll see it in parentheses, sometimes you won't. It's the same thing, okay? Then I'm going to do the 72. That splits 2 and 36, 2 and 18, 2 and 9, 3 and 3. And then I just have 1x, so that's going to be left over. So that's going to simplify 6 square root of 2x. Okay? When you multiply, you do outside times outside, radical times radical. Okay? So I'm going to have 4x squared times 6, which is going to give me square root of 2x times 2x is 4x squared. Did you really need that 4x squared? What should you have recognized? It's the same thing. What's the square root of 6 times the square root of 6, if I just gave you that? 6. Square root of 10 times square root of 10. 10. So this is really just 24x squared times 2x. But had it been a 2x and a 3x, you still need to do that. But since it's the same, if you can jump straight to this, I'm fine with that. Okay? Now, what is my final answer? 48x cubed. Are we good with that section? Okay. Now we're going to move on to rational exponents. Rational just means can be expressed as a fraction. So your exponents are now going to be fractions. Okay? Any exponential expression with a rational exponent can be written as a radical expression. So there's a formula that you have learned in Algebra 1, if I have a to the m over n power, which we've talked about this before. We've talked about this formula because that's why when you take a cube root, you have to have exponents divisible by 3. Y'all remember that lesson? Okay, so that denominator is your index. So I'm taking my base, raising it to the m over n. That's equivalent to the nth power of a raised to the m power. Okay? Now, you could go back and forth. You could also, if I give you this and ask you to rewrite it, you could go back and forth between the forms. Okay? This can also be written as this, but I typically go this route. Okay? Now, remember that if you have a negative exponent, if I have x to the negative 2, what does that negative exponent tell me? If I just gave you this, y'all remember that? X to the negative 2. We did a little bit of exponents in chapter 5. That negative exponent tells me it's in the wrong spot, so it would become 1 over x squared. Hopefully you remember that. Okay, that's a fundamental property for your exponents. So if I have a to the negative m over n, then all I'm doing is making this go into the denominator. It's still going to rewrite the same way, but now it's in the denominator because that negative tells me it's in the wrong position as far as numerator versus denominator goes. Okay? So be careful with that. Now, what we're going to do is we're just going to evaluate. So here, we're going to put it into radical form, and then we're going to evaluate it. Could you type this in your calculator and get an answer? Yes. But what is that really testing you? Can you plug stuff in a calculator? Not do you know the skill. Okay? So this is an easy way to check, but if you just give me one straight answer, you're not going to get full credit because you have no work to show for that. Okay? So if I have 16 to the 1/2, look at all three of these examples. What's the difference? The negative. Everything is the same. I still have 16 as my base. I still have 1/2 as my rational exponent. But the position, I don't have a negative here. I have a negative on the outside. Now I have a negative on the inside. We're going to see what happens with these three. Okay? So if I have 16 to the 1/2, how am I going to rewrite that in radical form? Square root of 16. Which is just 4. I'm not solving, so I don't need the plus or minus. Alright? Now, if I have negative on the outside, 16 to the 1/2, I want you to set this up on your own. Just set it up. What should it look like? Negative, then parentheses, square root of 16. That placement of your negative matters. Okay? So then, that means it's a negative 4. Now set up the next one. How should I have that set up? Which gives me. So you're going to have to be careful where you put those negatives. Alright, now, the next example, I've got 32 raised to the 3/5. So when I write that, I've got my radical. What's my index? 5. I'm taking the 5th root of 32, and then I'm raising that to the 3rd power. Okay? So what's the 5th root of 32? So I'm taking 2 to the 3rd power, which is 8. So you evaluate the radical, the nth root, and then you raise it to the exponent. Okay? So if I have 81 to the 3/4 power, I've got my radical. What's my index? 4. My base is 81. So I'm taking the 4th root of 81 raised to the 3rd power. So I expect to see each part. There's 3 parts to this. You rewrite it, you evaluate your radical, and then you raise it to the exponent. Okay? So the 4th root of 81, what is that? 3. So I'm taking 3 to the 3rd power, which is 27. Y'all good so far? Alright, now I have 64 raised to the negative 2/3. So it's going to be 1 over 64 to the 2/3. So I'm going to rewrite my denominator. It's the cube root of 64 raised to the 2nd power. So 1 over, what's the cube root of 64? So 1 over 4 squared, which is, so 1 over 16. Because we're about to get to a section where you have to work everything in rational exponent form, and then your last step is rewriting. So if you get in the habit of that, then it won't throw you off to that section. Okay, do we have questions for that section? We're good? Okay. Alright, so now we're going to look at solving using your nth root. So when you're solving, that's when you're paying attention to your plus and minus. Okay? So what we're trying to do is we're trying to get our x by itself. Okay? We're trying to get whatever is being raised to the exponent, which is our x for the first 2 examples, by itself. And then we're going to isolate that and then do the inverse. Okay? So if I have x squared, how do I undo x squared? Square root it. If I have x to the 7th, what do I do? Take the 7th root. Okay? Now, you're going to have to keep up with when do you do plus and minus and when do you not. Okay? So not every single answer is going to have a plus or minus. So if the index is even, that's when you have your plus and minus. If it is odd, you're just going to have your answer. Why is only even plus or minus? Huh? No one has a thought. Huh? What does that plus and minus tell me? Positive or negative? Okay, so why are only even indexes going to give me a possible positive or negative? Okay, y'all can't hear her, but yes. So if you take a negative and multiply it an even number of times, then you're always going to get a positive. So when I take the square root of 4, I could have multiplied 2 times 2 to get my 4, or I could have had negative 2 times negative 2 to still get my positive 4, right? If I were to take the cube root of 8, what is that? 2, all right? If I take the cube root of negative 8, what is that? Negative 2. But what if I took the square root of negative 4? Square root of negative 4? 2i. So why are we able to do the cube root of a negative but not the square root of a negative? Because a negative times a negative will always give you a positive. The same type of response in reasoning why only your even indexes are going to give you that plus and minus. Okay, y'all are going to have to broaden that bubble, not just be told something and put it back on paper. You have to understand why it's this way. If you can understand that fundamental concept, then you're not going to have to guess when do I do plus or minus and when do I not. Okay? So if I have 4x to the 5th equals 128, I want to solve for x to the 5th. What am I going to do? If I had 4x equals 128, just that, what would I do? Why? Because you want x by itself. Well, I want x to the 5th by itself. So I'm going to divide. I want to isolate that x to the 5th. So x to the 5th is equal to 32. And how am I going to get x now? You take the 5th root. If you are supposed to be taking the 5th root and you only write a square root, is that the same? No. Are you going to get full credit? No. Some of y'all are going to have to pick it up on y'all's details. Okay? There's a lot of people who lose careless points over not putting the right notation, not putting the right work. Okay? Now, that's going to give me x equals what? I could store 2 for x, type 4x to the 5th, it should give me 128. Okay? 5x to the 6th plus 36 equals 100. Subtract 36. X to the 6th is equal to, and then what do I do? The 6th root. So x is equal to plus or minus 2. I took an even root. I gotta have that plus or minus. Alright, now I have x minus 3 to the 4th equals 81. My x is no longer to the 4th. It's x minus 3 to the 4th. So what am I going to have to do here versus what I had to do over here? You're going to root it first. Now, what if I had a number? What would that affect? What if I had x minus 3 to the 4th plus 30? You subtract it. You still want whatever is being raised to the exponent, whether it's just x or x minus or plus something, you still want that by itself isolated, okay? So I'm going to start with the 4th root, and that's going to leave me with what? X minus 3 equals plus or minus 3. Now, do I just box it and I'm done? What do I have to do? So, I need to add that 3, x equals 3 plus or minus 3. I have two separate x values. X equals and x equals. You're going to have to be careful with that. Okay? Are we good with that section? Okay. Alright, properties of rational exponents. So, if you look at your handout, these are your properties of exponents. Okay? If I'm multiplying like bases, I add my exponents. If I am dividing number 5, I subtract my exponents. You should remember these. This should not be new material for you. If I have a power to a power, I multiply. You can only multiply exponent times exponent, okay? If I have two terms inside parentheses, so if I had a 2x raised to the 3rd, some of y'all struggled with this when we were doing transformations, okay? You're going to do 2 to the 3rd and x to the 3rd. So that's going to give me 8x cubed, not 2x cubed. There's a lot of people making this mistake. Okay? Now, this is my negative exponent that I've already talked to y'all about. We just talked about this one. And this 6 and 3 kind of go hand in hand. If you have multiple terms with one exponent on the outside of those parentheses, you're just basically distributing that outer exponent, okay? We're not going to look at this yet. Well, we can just talk about it. If you have the nth root of two terms being multiplied, you can just separate it. So if I had the nth root of 80x to the 5th, like whatever that example was earlier, you take, say, the square root of 80 and then the square root of x to the 5th. You separate them, and that's how you do it, okay? Same thing if it was division. So if it was the square root of 80 over x to the 5th, you would just separate square root of 80 over square root of x to the 5th, okay? This is not something to get confused about, okay? So if you have rational exponents, meaning you've got exponents, no radicals, and they're fractions for your exponents, your work should be all in rational exponents until the very last step. So you can't do anything else, okay? So what I mean is I'm not going to start by converting this to radicals. I'm going to start by using my properties of exponents, okay? So if I have 7 to the 1/4 times 7 to the 1/2, I'm multiplying like bases. So I am taking 7 and adding 1/4 plus 1/2. Well, 1/2 is the same as 2/4, so 1/4 plus 2/4 is 7 to the 3/4. Now there's no other simplifying I can do. So from this point, then I can rewrite it in radical form. Okay, this is going to be the 4th root of 7 raised to the 3rd power. Or, this is where, when I told you can write it as this or this. Okay, this is what we're going to be looking at in this section, because I can't simplify the 4th root of 7. So the only other way I'm going to simplify this is if I do the 4th root of 7 cubed. So the 4th root of, what's 7 cubed? 343. Now, I'm not going to break 343 down and try to see if I can make groups of 4. Why? Because there's only 3 sevens. Right? So if I only have 3 sevens, 7 is prime, I can't do anything with that. So this is going to be it. Now, this next example, I've got 6 to the 1/2 times 4 to the 1/3, all raised to the power of 2. We're going to get rid of this outer exponent first. So I'm going to distribute that 2 to each of those exponents. So I have a power to a power, so I can multiply those. So that becomes 6. 1/2 times 2 is just 1, so it's just 6. Times 4 to the 2/3. Okay, so my 6 is on the outside. That 4 raised to the 2/3, how am I going to write that? The cube root of 4 squared, which is the cube root of 16. Now, can I simplify that? Yes. I can take my 16, 2 and 8, 2 and 4, 2 and 2. I have a group of 3 with 1 left over. So that turns into what? What's my final answer? 12 cube root of 2. Y'all understand that? Okay. Alright, to the 5th, all raised to the negative 1/5. Up to you if you want to distribute first or change the position first. Okay? What do y'all want to do first? Change the position. Okay? So if you change the position, this becomes 1 over 4 to the 5th times 3 to the 5th raised to the 1/5. So when I distribute, that becomes 1 over 4 times 3. Because 5 times 1/5 is just 1. So my answer would be, there was no rewriting for that. Because my exponents just happened to have canceled to 1. Okay? Now I have 5 over 5 to the 1/3. What do I do with that? This doesn't have an exponent written. What is it understood to be? 1. What do you notice about the numerator and the denominator? They're like bases, right? I'm not rewriting. I need to use my properties. I divide like bases, so what am I doing with my exponents? 1 minus 1/3, which is 5 to the 2/3. Then I can rewrite it to be the cube root of 5 squared, which is just the cube root of 25. Are we good with that? Do we have questions? Okay. This is a lot. It's not hard, but there's a lot to it. Okay? Because once you get to your worksheet, it's going to be all together. Okay? Your properties of radicals. Basically what we were doing earlier, you're simplifying and then you're doing operations with it. Okay? Always, always simplify. Now, you cannot have radicals in the denominator, and you can't have radicands that contain fractions. Okay, we're going to split everything, simplify everything. If we have a radical in the denominator, then you've got to rationalize it. Okay, which should not be new either, because I know you did that in geometry when y'all did special right triangles. Okay. All right, so everything could be different. Every problem, you don't do the same thing every single problem. So if I have the cube root of 12 times the cube root of 18, I can simplify or multiply. What do y'all want to do? Let's say we simplify. Okay? So if I do 12, can I simplify that? Is that really going to be simplified? No, because I don't have groups of 3. Sometimes you can, sometimes you can't. Alright? So, what about 18? Could I do that? Not with a cube root. Okay? So, we're going to have to multiply. What's 12 times 18? 216. And let me tell y'all, before I start breaking that apart, I'm going to check, is that a perfect cube? Six. If you don't get in the habit of checking, you would have done a whole prime factor tree for 216 to realize every single prime factor pairs up. Okay, so get in the habit of checking. Alright, now if I've got the 4th root of 80 over the 4th root of 5, when I have fractions, I can kind of manipulate that. Okay? If I'm looking at my numbers, could I simplify 80 over 5? It ends in a 0. I can divide that. So I can really put this back together, the fourth root of 80 over 5. And that becomes the fourth root of what? What is 80 divided by 5? Which is 2. So if you have fractions like this, I would try to see, can I manipulate those bases? Can I manipulate the radicand? Can I simplify that fraction? If you can, do it. If not, then that's whenever you would do your rationalization. Okay? Now I've got 7 cube root of 27x squared times 4 cube root of 86. This is kind of like what we did earlier. Okay? I'm going to try to simplify the cube root of 27x squared. What is the cube root of 27? So, can I simplify the cube root of x squared? No. I need 3 and I only have 2. So this as a whole is going to be 7 times 3 cube root of x squared, which is just 21 cube root of x squared. Okay? Then I've got 4 cube root of 8x. So 4 times what? 2 cube root of x, which is 8 cube root of x. Alright? What's 21 times 8? 168. If I am taking cube root of x squared times cube root of x, that's going to give me the cube root of x cubed, which is just x. If you wanted to jump straight to this, you can. You should be able to. Alright. Cube root of 162 x to the 5th over cube root of 3 x squared. What do you want to do first? Okay, I want to put it back as 1. So I'm going to do the cube root of 162 x to the 5th over 3x squared. What's 162 divided by 3? 54. What's x to the 5th divided by x squared? X to the 3rd. Can I simplify 54? That's going to give me 2 and 27, 3 and 9, 3 and 3. So, what's my final answer going to be? 3x cube root of 2. Y'all good with that? Okay. Alright, rationalizing the denominator. Something like 4 square root of 2. What would I do there? Multiply by the square root of 2 on top and bottom, because you can't do something to the bottom without doing it to the top. That's your 1. And that becomes what? 4 square root of 2 over 2, which simplifies to 2 square root of 2. That's something you would have done in geometry. Right? Okay. Why are you multiplying it by the square root of 2? To cancel out the square root, right? So if I have the 4th root of 2 over the 4th root of 3, I can't have the 4th root of 3 in my denominator. I can't simplify 2 over 3. So I'm multiplying by what? If I'm multiplying by the fourth root of 3, is that going to give me 3? Okay. So we said if you multiply the square root of 2 times the square root of 2, it just undoes the root, right? Why? Because it's a square root. How many pairs do you need? Like, how many of what number to make a pair? 2. So if I'm taking the fourth root of 3, how many 3's do I need to make it? Okay. So you can't just multiply it by the fourth root of 3. You're going to need, I have one of them, I need 3 more, right? Now, I'm going to write this out, this first example, but you shouldn't have to do this, okay? I have one of them, I need 3 more. So I'm really rationalizing by the fourth root of 27. All right, so that gives me in the numerator the fourth root of, what's 27 times 2? 54. And then my denominator, there's my 3. Could I simplify 54? Number sense, y'all. We got 3 3's times a 2. Look at what you're given before you start wasting your time breaking it down. Okay? It's going to have to stay like this. Alright? Fourth root of 3 over 4. I need to break that. So earlier, it was already broken, and we wanted to put it together to simplify. Here, 3 over 4 can't simplify, so I'm going to break it fourth root of 3 over the fourth root of 4. I want you to try this one. What do I do? Did everyone do that? Did anyone not do that? Okay, so then that gave you what? The fourth root of over. Did you leave it like that? You shouldn't have. 192. What does that break into? Do what? You did 16 and 12? So that would have broken down into what? What? I can't hear y'all. Four, yeah. So 2 fourth root of 12 over 4, which is fourth root of 12 over 2. Everyone did that. Alright, now, I'm going to do it in a color y'all can see. That's a 4. All my numbers are not working today. Okay, the fourth root of 4. Hey, what can be multiplied by itself to get 4? You could have rationalized by the fourth root of 4 with 2 more 2's. Right? I could have broken down 4 into 2 and 2. I have 2 of my 4. So I could have gotten the fourth root of 12 over 4 over 2. Because I did 4 2's. Be careful when you have perfect numbers in your denominator. You can always break it down. 3 and 3. You don't have to, but look how much easier that is. So if you have perfect squares or perfect cubes or any of those perfect numbers, try to train yourself to break that down so it's less you're having to do side work. Now if you did this, you got all the way down here, that's correct. But there's an easier way. Okay? Alright. Fifth root of 7 over 8. Do that one. What do I rationalize by? The fifth root of 4. Why? 8 is a perfect cube. So you could have split that. There's 3 of my 5, right? So I need how many more? 2. So 2 times 2 gives me 4. There's my other 2. So the fifth root of 4, my numerator is going to become the fifth root of 28. My denominator is going to become 2. Can the fifth root of 28 be broken? No. How many multiplied by 4 eighths? Did y'all all start like this? I have a feeling no, because there was a lot of moving around with these pencils when I started this. Okay. Alright. I've got one last example. The 5 over 4 minus square root of 3. This shouldn't be the first time we're doing this. I multiply by its conjugate. 4 plus square root of 3. So my numerator, a lot of people kind of struggled when we did this. You have to distribute. 5 times 4 gives me 20 plus 5 square root of 3. Now, my conjugate formula tells me if I have a minus b times a plus b, then that gives me a squared minus b squared. So 4 times 4 is 16 minus 3. So my final answer would be 20 plus 5 squared root of 3 over. Okay? We good? Do we have questions? Okay, y'all have a quiz over this.